Okay, good day. This is dual enrollment pre-calculus, lesson number 5, polynomials, graphs of polynomial functions, and behavior. I am Mr. McCulley. Let's get to it. Today, lesson 5, our learning goals have come from section 2.2 in the text. We're going to use transformations to sketch graphs of polynomial functions. We're going to use the leading coefficient test to determine the end behavior of the graphs of polynomial functions. And we're going to find and use the zeros of polynomial functions to sketch their graphs. And we're going to use the intermediate value theorem to help locate zeros of polynomial functions. So let's get to it. Polynomial equations, they look sort of like this. If you talk about the quadratics that we talked about in the last section, if we just talk about this, ooh, I wanted a much bigger, let's see here, give me a size, there we go. If I wanted to talk about just a quadratic function, we're talking about that. And if we wanted to talk about a linear function, we would just talk about that portion. Y equals mx plus b. And so when you see this kind of an expression here, it's talking about any polynomial function that can take up any form. And the reason that there's these 3 dots here in the middle is because I do not know how big n is, but it could be any number as long as it fits the rest of the constraints here. So all of the terms have the form a sub n x to the n. Even this constant term, if it's a sub 0 x to the 0, we remember that anything to the 0 power, remember x to the 0 is equal to 1 provided that x is not equal to 0. A sub n is a coefficient, so a sub n minus 1, a sub 2, a sub 1, and a sub 0 are all coefficients. The highest power any term of the polynomial determines the degree of the polynomial. So if we saw something like this, y equals, let's say, x to the 5th minus 3x squared plus 2x minus 1, then we would say that this thing has a degree of 5. The constant term is always the term that has no variable, and again, that's because anything to the 0 power would just be 1. N must be a whole number for the function to be a polynomial. If it's negative, if it's a fraction, that's all I can really, possibly a decimal, then this is no longer a polynomial function. That's all I have to say about that particular section. Polynomial function graphs are always continuous. They are smooth curves. That does include linear equations are considered to be curves. They have no holes and they have no sharp turns. So what does a hole and a sharp turn look like in a graph? Well, you could potentially have a graph that has a small gap in it called a hole. The graphing calculator will not show these things. And so that's one limitation of the graphing calculator. It will show these gaps if there's possible. And here is an instance of what we would call a sharp turn. And we can get a sharp turn fairly easily. Let's just do one real quick here. If I go, let's clear this stuff out from last time. Let's say I go parenthesis, I go second, I go, let's see here, square root of, let's clear this out. I got it. Let's go second, square root of second. No, let's just go math. Let's go over to number. Here's the absolute value. Absolute value x. Okay, this is not a polynomial function. And if I hit graph here, let's go back to a standard zoom. Zoom 6. There we go. There's an instance of a sharp turn. Comes in real smooth, sharp turn there and goes on. But definitely not a polynomial function. Doesn't fit what we had there. All right, let's talk about the end behavior. The end behavior is called the leading coefficient test. If you were in my Honors Algebra 2 class last year, I did the polynomial shuffle for you. Unfortunately, this medium does not allow me to do that. But essentially, the leading coefficient test tells you that you can determine what the end of the function is doing as you go to extreme x values based on the highest degree term and its leading coefficient. And so when you look at the graphs that I have here, where I have this black and this little blue, I can't really use the leading coefficient test to tell what's going on with the blue portion, but what I can tell is what it's doing at the extreme values. So if the degree is even and the leading coefficient is positive, then this function is going to go up as x goes to negative infinity, and it will go up as x goes to positive infinity. If the degree is even and the leading coefficient is negative, then as x goes to negative infinity, the function will go down, and as x goes to positive infinity, the function will also go down. The third option is if the degree is odd and the leading coefficient is positive. If that's true, as x goes to negative infinity, the function will go to negative infinity, and as x goes to positive infinity, the function goes to positive infinity. And then if the degree is odd, then the leading coefficient is negative. As x goes to negative infinity, the function goes to positive infinity. And as x goes to positive infinity, the function goes down to negative infinity. And so just a real quick graphing calculator example of this. If you look at just a real simple graph, let's say we made it let's just say 2x squared. That is a polynomial function. And you know what? Let's throw something else in there. Let's throw in minus 6x, I guess. That works. So this polynomial function of degree 2, that means the degree is even, and its leading coefficient is positive. So our end behavior would tell us that this thing goes to positive infinity as the x values go to negative infinity and to positive infinity. If we hit graph, we can see that as we go to the left, the function goes up, and as we go to the right, the function goes up. Now, the moment I make this just negative, we'll change it to -2. Now that's going to change the shape a little bit. But we clearly see as x goes to negative infinity, the function goes down, and as x goes to positive infinity, the function goes down. So we have an even, let's see here, where is my equation? There it is. We have an even degree polynomial because it's x squared, and we have a leading coefficient that's negative even though the cursor shows that it is not, and we get a graph that points down to the left and right. If I hit my y equals, and it just all we would have to do is let's make this back to a positive, so we'll delete that. I don't want to do that. Let's hit delete there, and let's change this exponent to an odd number, say a 3. Let's see what that gives us. Oh, that looks nice. And again, as x goes to negative infinity, the function goes down. As x goes to positive infinity, the function goes up. We know that because we hit our y equals, our degree is odd, and the leading coefficient would be +1 in here. And again, we can just change that to be, if I hit insert and I hit a negative symbol there, hit my graph sign, again, we see up to the right, down to the left, or up to the left, down to the right, which is what we're looking for. Okay, some terminology for zeros of a function. If a function f is a polynomial function and a is a real number, then the following statements are equivalent. X equals 0, a is a 0 root of the function. All right. X equals a is a solution of the polynomial function f of x equals 0. X minus a is a factor of the polynomial f of x. And x0 is an x-intercept of the function. So when you say that something is a 0, all of the other 3 conclusions can be made, and vice versa. Anytime you choose any one of these statements, the other 3 have to also be true. Multiplicity for a polynomial function of factor x minus a to the k yields repeated 0 x equals a of multiplicity k. If k is odd, then the graph crosses the x-axis at a. If x is even, then the graph touches, and there should be a space here, touches the x-axis but does not cross the x-axis at a. All right, so what does that mean? Well, yeah, and again, let's go to the graphing calculator here real quick. Clear this out. Let's talk about two factors. Let's say x minus 2 and hit quantity. Ooh, I want to put a parenthesis there first. So let's delete that. Let's delete that. Let's put parenthesis and hit squared, and then hit times. Um, let's go x plus 3, so we will be able to discuss both of our, and let's just leave that as 1. And so when I look at this thing, based on that last slide there, the 0 of this particular polynomial is positive 2 and negative 3. Those are your zeros. This 0, positive 2, has a multiplicity of 2, and this 0, x equals negative 3, has a multiplicity of 1, because that's the degree of that 0. So when I hit graph of that function, at negative 3, because it's an odd numbered multiplicity for 0, just 1, 1 is an odd number, it goes through the x-axis. Since x equals 2 is a 0 of the function with multiplicity of 2, which is an even number, it just comes down and touches the x-axis. Now, the same would hold true if we came back over here and raised this to the third power. Now, it's going to make everything a little bit steeper, but if I go to the third power, that's still going, oops, sorry about that, that's still going to have an odd multiplicity there. So when I hit graph, it goes through the x-axis at negative 3, and it still just touches the x-axis at positive 2. All right. Getting into some examples. Use the parent function to describe the transformation and graph the function. And so I'm going to say my parent function is f of x equals x to the third. And so if I am describing my transformations of this thing, and this goes back to our transformations from one of the earlier lessons, if I plug a number in, what's the first thing that happens? I subtract 2 from it. So let's say I said x equals 4. I'm going to plug in 4. I'm going to subtract 2. That's a left-right transformation. And because it's negative, remember, inside, left-right transformations are opposite what we would think it would be. So we're going to say that our g function is going to be transformed to, let's say it's translated here, translated 2 units to the right. And this one, and then after I subtract 2, I'll raise it to the third. That is our function. And then I'm going to subtract 3 from that. That is going to be a translate 3 units down. All right, so f of x equals x to the third has 3 real simple values that I can plug in. If I plug in negative 1 to the third power is negative 1. 0 to the third power is 0. 1 to the third power is 1. Now we'll be off the chart here, but if I go negative 2 to the third, I get negative 8, which would be below there. And then if I go 2 to the third, that would be positive 8. So I'm going to get something that ends up looking like this. But if I know a couple of points, and I know that this is a static transformation, all I got to do is move the points 2 to the right and 3 units down. So negative 1, 1, 2 to the right, 3 units down. So 1, 2, no, that's where I started. 1, 2, 3 would be there. 0, 0, 1, 2 to the right, 1, 2, 3 down. 1, 1 will go 1, 2, 3 to the right, or no, excuse me, just 1, 2 to the right, and then 1, 2, 3 down. And all I got to do is match this shape. I get a graph that looks like that. So there is my change of shape transformation. And again, you're always welcome to grab your graphing calculator and check your work. And so I had x minus 2 raised to the third, and then it was, bring my arrow down there, minus 3. And I hit graph, and clearly we see something that looks like what I had just done. All right, next example. So do the following functions have the same end and behavior? Why or why not? Well, let's take a look at these things. I have f of x equals negative x to the, or negative 1/3 times the quantity x to the third minus 3x plus 2, and g of x equals negative 1/3 x to the third. Well, I can get rid of my parentheses by distributing and say that this would be negative 1/3 x to the third, and then negative 1/3 times negative 3 would be positive 1x, and then negative 1/3 times times positive 2 will be negative 2/3. All right, so does it have the same end behavior? Well, to do that, we use that leading coefficient test, and since the degrees are the same, they're both 3. All right, so it's going to have kind of a similar shape, and the leading coefficients are the same. We can say yes, both f and g will have the same end behavior because they are A-R-E of the same degree, and that degree was 3, and their leading coefficient, um, abbreviate there, has the same sign. And in this case, that same sign is negative. All right, next example here. All right, it says use the leading coefficient test to describe the left and right hand behavior of the polynomial function. I picked this one for a couple of different reasons. The big one is I wanted to review with you guys a common error made by students when they see something that looks like this. Notice I have a polynomial expression all over 4. And the reason I wanted to use this as an example is because you have to remember that when you add or subtract fractions, you have to have a common denominator. So we can rewrite this thing where we have all 4 of those terms all over 4. So we can rewrite this as 3/4 x to the 7th minus 2/4, which will make 1/2 x to the 5th plus 5/4 x to the 3rd, and then 6/4 reduced to 3/2 x squared. So our leading coefficient test. So here's how we're going to describe the left and right handed behavior, the right and left-handed behavior. So we're going to say as x goes to positive infinity, we are going to conclude that f of x goes to something. And as x goes to negative infinity, f of x also goes to something. Well, my leading coefficient, or my degree, is 7, and that's an odd number. And my leading coefficient is 3/4, and that's positive. All right, so if you go back to that little chart I gave you, leading degree odd, leading coefficient positive, you're going to get a graph that looks something like this. Probably has a little more bumps in the middle, but all we're talking about is the leading coefficient. So as x goes to positive infinity, that will be this way, the function goes up. That's also to positive infinity. And as x goes to negative infinity, the function goes towards a negative infinity. So we had a negative infinity there, put a box around that, and we are finished with that example. All right, find the zeros algebraically, and then use a graphing calculator to verify the zeros. That's number 42 from the text. Let's check out that number. I had meant to put this in here, but let's grab it. So it's f of x equals, let's see here, we get x to the 5th minus 6x to the 3rd, and then it's plus 9x. And so we want to find these zeros algebraically. We're going to do it through factoring. There are other methods, but this one seems to work good. First, I'm going to use greatest common factor. In this case, it's just x, and divide out x. And that'll give me f of x. I guess I didn't need to put it equals there. I'll get x, and then in this have x to the fourth minus 6x squared plus 9. This is quadratic form. And so I have to ask myself, I need two factors of positive 9 that add up to negative 6, and that's fairly easy. Or positive 9 that add to negative 6, negative 3, and negative 3. So I've got x, it'll be x squared minus 3 and x squared minus 3. This is irreducible over integers. So just because all of these are integers, but we could possibly go down. So this is one possible answer. And then we could reduce to irrational numbers and say x. We could go x minus square root of 3, x plus square root of 3. That would be the factors of this first one. And since they're the same, we could do it again. X minus square root of 3, x plus square root of 3. And we have two double roots, x minus is there and x plus right there. So if I go to my graphing calculator and I type in what we had, it was x raised to the fifth, and then it was minus 6x raised to the third, and then it was plus it was plus 9x, sorry, 9x. If I hit graph, our 0 at 0 is right there. Square root of 3 is not quite 2. It can't be 2 because 2 squared we know is 4. So square root of 3 and then 1 squared is 1. So somewhere in between there, closer to 2 than it would be to 1. There's my negative square root of 3, and then there's my positive square root of 3. So these are fine. So finding the zeros, gotta make sure that we answer the question. These are the factors, by the way. So the zeros are going to be 0. That's a 0. When I plug in 0, I get a 0 there. When I plug in square root of 3, I'll get a 0 here. And when I plug in negative square root of 3, I'll get a 0 right there. And again, talk about multiplicity on the next one. Find all of the real zeros and determine the multiplicity of each zero. So number 56. They give us this thing. They say f of x is equal to x to the fourth, and then it'll be minus x to the third, and then minus 20x squared. So again, we're going to find GCF. You should always check for GCF. Sometimes you find them, sometimes you don't. And in this particular case, what's common to all of those terms? I don't like this sign there. All right, we'll rewrite. X to the fourth minus x to the third, and then what was it? Minus or plus? It was minus. Okay, that works. In the GCF, what is the greatest common factor to all three of those terms? In this particular instance, it's x squared. And so I've got f of x equals x squared, and then x to the fourth divided by x squared is just x squared. X to the third divided by x squared is just x. And then negative 20x squared divided by x squared is negative 20. And so we're going to factor this. And so two factors of negative 20 that add up to negative 1, that's fairly easy. You've got negative 5 and positive 4. So we'll get x squared, we'll get x minus 5, x plus 4, and again, we're just keeping this short, so when I multiply these together, I will get that original one back out. So my zeros And then we're going to put my multiple, we're going to make it a little table. So I've got zeros. What makes x squared 0? Well, 0 makes x squared 0, so 0 is a 0. What makes x minus 5 0? Well, 5 makes that 0. And what makes x plus 4 0? Well, negative 4 makes that 0. So how many of those zeros are there? Well, since it's x squared, we could factor that to x and x. That gives it a multiplicity of 2. Now, x minus 5 is just a first degree 0, so it has a multiplicity of 1. Same thing with x to the 4, or excuse me, x plus 4. So since that's also to the first power, it has a multiplicity of 1 as well, and that is our answer. Final example, or final two examples, it says find a polynomial with zeros, 0, 1, and x. Okay, so first thing we're going to do is write the factors. All right, so if my 0 is 0, my factor is x. If my 0 is 1, my factor is going to be x minus 1. And if my 0 is 6, then it's going to be x minus 6. Now we're going to, and after we've written our factors, we're then going to multiply. Now the good thing about multiplication is that multiplication is commutative, so we can multiply in any order that we want. And I would suggest multiplying the harder two factors first, because all we got to do is distribute the x once we're done. So that's the easy one. So let's multiply x minus 1 and x minus 6 together first. That'll bring my x down there. X times x is x squared. X times negative 6 is negative 6x. Negative 1 times x is negative x. And then negative 1 times negative 6 is positive 6. I'm going to collect my like terms. That'll give me x times x squared minus 7x plus 6. And then we'll distribute x. And that'll give me a final answer of x to the third minus 7x squared plus 6x. There we go. All right, so find a polynomial with the given zeros and multiplicities. So I have a 0 of 3 for this one and a multiplicity of 1. That's going to give me, so again, I'm going to write the factors. And then it'll be with correct multiplicity. And so if the 0 is 3, then the factor is x minus 3, and I only have to put that down one time. And so x, if the 0 is 2, then the factor is x minus 2. And since that has a multiplicity of 3, I have to put that down 3 times. Oops. And so multiplying this out, there's a shortcut, but if you go x minus 2 times x minus 2 times x minus 2 times x minus 3, I can do the x minus 2's fairly quickly in my head. Let's see here, I'm going to get x to the third, and then it will be minus 3x squared. No, that's wrong. Don't mess up. Let's see here, it'd be minus 3 times x squared times 2 plus 3 times x times 4, and then it'll be minus just 8, which will give me x minus 3, x to the third minus 6x squared, plus 12x minus 8. And then when I distribute all of this out, I'm just going to stack, multiply and stack. So x times x to the third is x to the fourth, x times negative 6x squared is negative 6x to the third, x times 12x is 12x squared, and then negative 3 times negative 8 is 24. Negative 3 times x to the third is negative 3x to the third. X times negative 3 times negative 6x squared will be positive 12 Let's do it right. Positive 18x squared. Negative 3 times negative 12 is negative 36. And then I need an x for that. And then negative 3 times negative 6 is positive 24, giving me a final function, f of x equals x to the fourth minus 9x to the third plus, let's see here, 12 and 18 is 30, x squared minus, let's see here, 60. 60x and then plus 24. I think that's right. Quick, if you have any arithmetic errors, I apologize, and we can discuss it in class. All right, that's all I got there, folks. So we are to the Star Wars fun fact of the day. Tupac Shakur auditioned for the part of Mace Windu in The Phantom Menace, but the part eventually went to Samuel L. Jackson, and that ends up being because unfortunately, Mr. Shakur perished before he even got the chance. That's all I got, folks. Have a good day. Goodbye.